is goed. Gaan we hier naartoe. Poepedoedoe. Refresh. Oké, hier naartoe. We zijn live, ja, dat gaat goed. Oké. Okay, students, welcome to the 12th lecture on multibody dynamics. And yeah, if you look at the schedule, then initially we had 13 lectures planned, but this will be the last lecture today. So lecture 12, the last. So the last lecture, which was initially scheduled for next week, will be cancelled because we covered enough material with today's material, and it's already difficult enough with all these corona measures to do the studying. Okay, the topic of today is actually the last chapter of the book, chapter 20 on complex 3D multi-body dynamic systems. And I think the best thing is to, by means of an example, a simple example, I will show the different strategies you can take, how you can set up equations of motion for such a complex system. I will not set them up in detail, but I will give just the general layout to do that. In the book there's also an example that's far more complex. There are constraints and regular constraints, holonomic and non-holonomic constraints. So if you are interested, you can read the book, chapter 20, for a more complex problem. The complex thing I'm going to treat today is rather simple, but it shows you the route to go. One route to go, by the way. Okay, but before we start, so I expect that maybe I don't need the full 2 hours of lecture, but let's see. I will keep the scheduled question and answer after the lecture. Okay, but first we start with Kahoot, right? Kahoot, yeah. So everything is running. Let me check. Yep, that's good. Okay, Kahoot, where are thou? Is Kahoot, yeah. Good in the picture. This we're gonna do, number 12. Teach, I don't know why I pressed teach, but that should be right. We're classic, we're not team. Yeah, okay, get your phones and your machines ready. That is the pin. I see in the YouTube, oh, that's pretty constant. 92 people are watching the live stream. So on average my expectation is 107 participants, 107, my guess. We'll just wait until we see most people are in. Oh, it's a bit lower. 94, 95, 96, which is the number of watching on YouTube. Okay, so my guess is that most people are then watching individually. Oh, 97. Okay, let's go. 5 questions on the content. You see 13, but that's another thing. Just 5 on the content. No worries. And it's 60 seconds. Because most of the questions are pretty simple. So this is about gimbal lock. I talked about last week. So when does gimbal lock happen? Gimbal lock being this singular configuration where you are unable to determine what the angular speeds are and the rates of the angles, Euler angles versus the angular speeds. So we have to be a bit more quick today because it's all 60 seconds. Questions are not so difficult. Okay, so the numerator is right, so it's the middle one, right? So beta, if we look at the, we start with alpha, beta and gamma, it's always the middle one which gives you the gimbal lock. If this is plus or minus 90 degrees, then A and C are aligned and then you're in trouble. Very good. Okay, next question. Constraint on the 4 Euler parameters is... So of course we only need 3 parameters according to Euler theorem, but with the 4 Euler parameters there's a constraint. What is the constraint? Yeah, indeed. They should be a unit length, right? So the norm should be 1. Very good. Okay, next question. The inverse, when you use Euler parameters, is described by the following set Euler parameters. So either you negate them, or you negate the vector part, or you scalar part, or you take 1 over the values. What describes the inverse of the rotation? Yeah, so this needs for some feedback. No, you couldn't take the inverse of these values, because then this can't be right, because if you then take the norm, it's absolutely not 1, the sum of the squares. So why is blue the correct answer? Well, if you think about these Euler parameters, then this would be the axis times the axis of rotation, and it would be the cosine of half the angle. Now, but this is the axis times the sine of half the angle. So, but bear with me, if you change the direction of the axis by negating them, yeah, then you get the inverse rotation. You could also think this is with cosine half of the angle, this is with sine half of the angle. If I change the angle to minus, then this one doesn't change, but then this one changes. Read all about it in the book. Okay, next one. How many independent parameters are there? Now we go out into some imaginary space, a 4-dimensional space with 4 base vectors and 4 coordinates. So we have a rotation matrix of 4 by 4. And how many independent parameters do we need to describe that rotation matrix? Four, 6, 8, or 9? Think of how many constraints you have on the rotation matrix in a 4 by 4 dimensional space. Indeed, the correct answer is 6. Just by counting, 16 minus the number of constraints, and the number of constraints you just have to do the upper triangle and the diagonal. But from a physical point of view, with 4 base vectors, I mean, you can build 6 planes. Okay, next one. That's the last one on the content. So the angular velocity matrix, which is this W, this matrix, which is R dot times R transpose. It's a matrix. What is the matrix? Is it symmetric? Is it non-singular? Is it Hermitian? Or is it none of the above? Well, above, previous, all the other answers. I don't know. Symmetric, non-singular, Hermitian, or none? Yeah, it's an asymmetric matrix, it's a singular matrix, and a Hermitian, well, that's something with complex numbers and a transpose, and apparently it's none of those three, so it's none of the above. Very good. Now we continue our quiz, and not with content questions. The next questions, all the answers are correct, and for all the answers you get full credit. But it's for me to know your opinion about the course and about the things we did in the course and about the live stream and the TAs and so on. So you get full credit irrespective of your choice, and please finish that. Well, you have to finish that to get the full grade for the quiz, right? Okay, and your sincere answers are appreciated. Okay, next. The answers are short. I think I put them on 30 seconds because it's pretty quick. First, did you keep a detailed record of your homework assignments? No, sometimes, mostly, yes, always, yeah? On the minute. Just pick an answer. I will not hold it against you. Fully anonymous, right? Okay, yeah. See a nice distribution, right? Okay, next one. In doing the homework assignments, the TAs were very helpful, not so helpful, rather confusing me. It's really like Jana and Take, if you look at them. So Jana is explaining Take, or Take is explaining Jana. I don't know. Okay. Thank you. Next. If there was no live stream, then I would be. Very unhappy. Unhappy. Indifferent. Yeah, happy. Yeah, okay, very good. Most of you are very unhappy until unhappy. Some are indifferent. That's what I expected. No surprises. So I'm looking forward to the surprises actually. Yeah? Am I on the wrong track with something? Recorded lectures were used and very useful. Used and some sort of useful. Used but not so useful. Actually, I didn't use them. Okay, not used, that's interesting. Okido. Number 10, we're almost there. The in-class quizzes gave me feedback on my knowledge level in the course. Yes. Well, mostly. Little. Absolutely not. Okay, very little. That's interesting. So I will follow up on that. So apparently the in-class quizzes did not meet their goal. Okay, that's good. That's good to see for me. Next. Where are you? The things I learned in the course were okay, expectation or above, that's good. Yeah. Okay, where are we? The time spent on average on the homework assignment was for me, so you have a little bit more time because you have to do the math. It's 4 ECTS and 4 times 28, it's a total of 112 hours. If we divide it by 12, then on average we have 8 hours a week, 8 hours per assignment. So the idea is that you spend like a day on the assignment on average, a little bit more, a little bit less. And I'm really curious what your experience is. Of course, those who kept track of their time, they can just look it up, right? Others have to use their memory. Memory is usually not so good. And I don't only speak of personal experience, but also even with younger people, memory is not always that good. Okay, so apparently the mass apparently the math was not so hard. Okay, so we're clearly above average here. Yep. Then last question, would you like to be a TA next year? Yes, maybe, no, never. Hmm. 7 say never. 11 say yes. So for those 11, please contact me if you're really interested. There's always room for TAs. Okay. Podium. Yeah. Ta-da. Flow. Very good. Get feedback. Yeah. Save the results. Show the feedback. Save the results. Direct download. Come on, guy. Yeah. Save to my drive. Go back here. Save. It's a bit slow today. Maybe they know it's the last lecture. Kahoot doesn't know, right? Saved. Okay. Everybody's happy? Yeah, this doesn't comply with the quiz. Well, anyway. Okay, thank you very much. Let's go back to the content for today. It's a bit longer, the quiz, of course. Okay. As I said, I'm going to talk about these complex 3D multibody dynamic systems, chapter 20 in the book. And after having done the code, so I'll think I'll do it by example. So the example I want to do is a more or less complex 3D system. It's something where you cannot determine what the motion will be out of your head. So it looks something like this. It's a disk like this, and then attached to the disk is some pendulum thing, so something like this. Yeah, that looks about right, I guess. Yeah. Oh, and here we have, of course, the rotation. Yeah. Okay. So the disk, right? This is a disk, and then the disk in itself is rotating with respect to the inertia. Then on the disk, mounted on the disk, is one hinge, and that is in this direction, right? And then perpendicular to that one is a second hinge in this direction, and mounted there is a pendulum, and I give it some finite width, so you see. So this is the pendulum. Okay. Yeah, then this is the center of mass of the pendulum, and of course this is the center of mass of the disk, right? Then we need some coordinate systems. Well, first of all, there's this inertial system, and I think I picked these as the directions, yeah. So this is the inertial system, X, Y, and Z. Sometimes people write capitals, that's okay. And then, of course, here we have a hinge with a rotational angle alpha, and then attached to this disk is another coordinate system, the body fixed one. Let's put a B to that, right? So here, and we call it B1 because that's body 1. And again, X prime, and then this will be Y prime, and this will be Z prime. That's identical, because this is the axis of rotation. Then we have these two hinges, and of course this is the hinge is beta, and this, of course, you would expect it is gamma, and everything is clear about the directions, right? So we need some more coordinate systems, because we need a coordinate system for this body fixed system. So let's say in this initial hanging down configuration, and maybe we have also have gravity here, we have so this is body 2 and this is body 1. Then I have a body 2 coordinate system, and exactly with X prime, Y prime, and Z prime here. And for this, I like to know what these equations of motions are. So I want to know equations of motion, and clearly, yeah, okay, let's not be specific. So how do we get the equation of motion? Now there are various routes we can take, right? For this equation of motion, one way would be, so EOM, one way would be just a differential algebraic approach, right? So we We formulate the equation of motion of every individual rigid body, and then we formulate the constraints. We have 3 hinges, so the 3 hinge constraints, and then we get our coupled set of differential algebraic equations. Now let's do some counting. If we have 2 bodies, then the number of coordinates we have is, for everybody we have 6. So we have 2 times 6 is 12 coordinates, right? And also 12 speeds, of course. Then how many constraints do we have? We have 1, 2, 3 constraints. So we have 3 times, and the constraints are, the constraints are hinge constraints, meaning that there's only 1 degree of freedom left in the system. So we need to formulate 5 constraints, and 3 of them are this point of the body is in the origin, and then there are 2 constraints that 2 relative rotations are 0 and 1 relative rotation remains. So in total there are 5 constraints. Now we have 1, 2, 3 of these hinges. So 3 times 5, yeah. So we get how many? 15 constraints, right? So then how many degrees of freedom are there remaining in our system? Yeah. Okay, next approach. We could do a Lagrange approach. So we could do Lagrange, right? What does Lagrange say? Well, Lagrange tells us that we have to look for the independent generalized coordinates. Now, if I look at the system, of course we have 3 bodies in that sense, but anyway. If I look at the independent coordinates, then what are these independent coordinates? Well, looking at the system, what do I see? I see actually, yeah, there's 1 joint here, there's 1 joint here, and there's 1 joint here. Meaning that I have 3 independent coordinates, and in this case I can depict them. I can say they're alpha, they're beta, and they're gamma. Of course this is a 3, this is 18, of course 18 minus 3, I have 3 degrees of freedom. Oops, 18. Now I can write everything in terms of these alpha, beta, gamma and the alpha dot, beta, gamma dot. But we have seen if we do that, then we have to write down the kinetic energy, and we have to write down the potential energy in terms of this. These are lengthy expressions. We go up to the level of energy, and then to get the equations we go down again. And there's actually a faster approach, or more intuitive approach, and that is the TMT method. And again we use independent coordinates. Yeah. So again we use those 3 coordinates, the alpha, beta and gamma, but by means of the transformations we directly write down the equations of motion. So this is the route I'm going to take for today. So if you're interested, you can do this one, or you can this one, but this is the one I'm going to talk about now today. Okay, so what do we need for our TMT method? So TMT approach. Well, first of all, everything starts, of course, with virtual power, right? So we need an expression for our virtual power. And that is the virtual power where we sum up over all the bodies, and I say bodies with a B. I sum up all the bodies of the virtual power of the Newtonian equation of motion yeah, for every body plus the virtual power, the Euler equation of motion of every body. Because we can really distinguish between the translational part and the rotational part. And the sum of this virtual power is, of course, the two. Okay, does that look like? Let's see. So that virtual power is the sum over all the bodies, and the B is the bodies, of, well, first we take the virtual power of the Newtonian part. So let's do a big bracket. Newtonian part is pretty straightforward, right? We have applied forces at the body, and then we have minus the inertia forces, and I just write a capital M for the mass matrix. Then for the coordinates of the center of mass I write just x, so I should specify that, times the virtual power transpose of that body. So let's write down here what we mean actually. So we mean with the xb, that is the coordinates of the CM in the n frame, because everything about Newton equations have to be formulated in the inertial frame. So you could say that is the x and b. But I dropped the n, I don't want to do too much writing. Okay, so that is defined, applied forces, inertia forces. And then of course we need the Euler part of all these things. That's a bit more lengthy, because what do we get for the Euler parts? Well, first of all, we have applied torques, and I'm going to write it down in the everything in the body fixed frame. Therefore I use this accent. Officially I should use, of course, all these subscripts, so I'm going to write everything in the omega and an omega prime b. I'm going to, those are the angular velocities, right? Angular velocities in all the body fixed frames, and that's in body B fixed frame, right? So officially I should write omega and then b with a small b, and that's it. Or maybe the small b is also here, whatever. But I'm going to use this shorthand notation with the prime. So, and there's another thing. Oh, this is a dangerous band. Oh, yeah. So let's say again, and that's probably you also have these dangerous bands in your homework. Dangerous band. What is the dangerous band? Well, I have a mass matrix MB here, and I have applied torques MB prime here, and they look alike, but they're of course totally different. Anyway, okay, then I have all the inertia contributions, and that is of course for the Euler equation a bit more complex. So we have the mass moments of inertia matrix for every body, expressed in the body fixed frame, times the angular accelerations of that body, and then plus we have all these how do I call them? Convective terms, yeah, cross, and then these guys. This was the angular momentum, right? Yeah, and then we're done. This is closed, and then we're done with this bracket, and then we have the virtual angular velocities of the body. Wow. Yeah, and then we close this one for the summation. So we have to do for everybody this part and this part. And then, of course, we have to express our accelerations and our virtual displacements and our angular accelerations, angular velocity, and virtual angular velocities in terms of these independent generalized coordinates. Okay, let's do that step first. The expression into the generalized coordinates. So let's start with the Newton equation. So for the Newton equation, what do we need? Well, we need to express are the coordinates of our bodies in terms of our degrees of freedom, right? So that is just for every body, I have a transformation matrix. Or a transformation function, sorry, not a matrix yet, that will come. And remember, my q's, should I underline them? Yeah, because it's a vector. My q's are my generalized coordinates alpha, beta and gamma here. So I can express all my positions in terms of these q's. Now, let's go back to our picture. Can I do that? That's the first question. So, can I express the center of the disk of body 1 in terms of our alpha, beta, gamma? Yes, because it's constant. It doesn't change. That's easy. Can I express the position of this body in terms of our alpha, beta and gamma? Yeah, if I know what the radius is of the thing, right? And if I know what this distance is, this distance, let's call that d, then yeah, with the alpha I can determine where this position is, even when the thing is rotated, and when this position is given, that's with cosine alpha and sine alpha, then I know the relative position of this point with respect to this, it depends on these two angles, and then finally I can express the position of this point as a function of these dimensions and these three angles. So yes, in principle I could. Okay, so I have my positions. Given that, I have then my speeds, and that's simply differentiation, yes, right, with respect to my generalized coordinates times the speeds. And of course then I immediately have my virtual speeds, which I need for the virtual power expression, which is again this linear mapping, this transformation matrix. Now it is a transformation matrix. And then for the accelerations, which I need into the equation of motion, I can write again this transformation matrix times the accelerations plus all the convective terms and q dot. And I think I use a shorthand notation for that, otherwise it becomes very, very lengthy what I have to write. So I call this H, HB. So those are convective terms. Convective terms. They're just state-dependent accelerations. This depends on the angles, and they are just the speeds, but that is the state. But this mapping is important. So let's x double dot b equals. So this is the one we're going to use. That's what we're going to put into the equation of motion. So that's the Euler part. That's the Newton part. Now we go to the Euler part. Now what do we know about the Euler part? Well, for the Euler part we need angular speeds, right? And we need to express our angular speeds in terms of our angles, our generalized coordinates, in this case angles, our generalized coordinates, and their time derivatives. Or in other words, we have to write down our omega of every body in the body fixed frame, as a function of generalized coordinates and speeds. Now we have already seen that this is always a linear mapping, and this always is a linear mapping, so I have to write it as a function of q and q dot, but we know that's always linear, so we have a matrix B for every body, which is a function of the coordinates only, and times the generalized speeds. So this always holds, right? Because angular velocities are linear into the time derivatives of the generalized coordinates. Always, this is always linear in q dot. Therefore we can write it like that. Then for the virtual velocities, well, that's super simple. That's just again this matrix times these virtual velocities. Nothing changes there. We just put a strange symbol in front of it, either a sub thing or whatever. We use a delta here, but it has nothing to do with differentiation. It's just virtual. Then for the angular accelerations, what do we write there? So we just have to differentiate this expression, right? So we keep this first constant, bb, times q double dot, again the same Jacobian, plus then we have this linear mapping differentiated with respect to q times q dot, and again these are convective terms, and I'm gonna rename them in some simple, because the outcome is just simple a vector. So bb q double dot plus, and I called them g, okay, gb, and we call these convective terms, these guys. Yeah, just depending on the angles and the speeds. Okay, so that is the stuff we have to do. Then we have to substitute these in the virtual power expression, yeah, and then take that should hold for all virtual velocities, yeah, as long as they're not zero. Do I use an index? No, I can use a vector. And if I do that, then I get the equations of motion as many as we have q's, right? So for every q I get an equation of motion. However, these q's are tied together these equations of motion are tied together. They're not independent. You cannot say, oh, there's one for alpha, one for beta, and one for gamma. They're tied to this complex mass matrix thing. Okay, now to do that, what do finally the expressions look like? So what do we get? Well, first of all, we get a sum, because we have to sum over all the bodies. And then the mass matrix has two contributions, of course, because it has a part which has to do with the linear motion, and it has a part which has to do with the angular motion, but everything is condensed to these degrees of freedom. So the first part, we have transformation of the coordinates times the mass matrix of that body times this guy, and this is a transpose, of course, so this is the Newtonian part. And then for the Euler part, we also have mass contributions, and it's this B matrix times this B, body B, then I prime, remember, and then again this Jacobian B, this matrix, and then we close our bracket, and then we say, oh, that's times q double dot equals. So this is actually our reduced mass matrix. It transforms the CM mass matrix and the CM mass moments of inertia matrices to our degrees of freedom. Then on the right hand side we have our generalized forces Q, and what are they? In our case they are this M, torque alpha, torque beta, torque gamma. They're totally dual to our degrees of freedom alpha, beta and gamma. So these are, like you say, applied torques in the joints. And then of course we get a right hand side which becomes pretty complex. Again, that's the sum over all the bodies of, well, first of all we have the Newtonian part, which is again this transformation matrix, remember, TBQ transformed times. Then we have the applied forces, FB, minus mass matrix B times, and then we have convective forces, remember, because we need to express the acceleration, and there we have the convective forces. And then plus, then we have a part which has to do with the rotation, then we get BB transforms times. Well, then we have the applied torques of all the bodies, and don't confuse it with the mass matrix, dangerous band, minus